And we are recording now. Okay, so we're recording on Screencast-O-Matic. This should be good. All right, so in order to talk about air pollution, we need to talk a little bit about the atmosphere. And you may be familiar with some of this information, but I do want to make certain that we talk for a moment. And can you see my red pointer? Hopefully you guys can see me pointing at the layers of the atmosphere that are on the left. We want to talk a little bit about the different layers of the atmosphere. You will be expected to have that information when you come into the course, and there's some really important aspects that you want to try to record and memorize, some things that are going to be important, particularly as we talk about the different types of air pollution. So let me start over here by just analyzing how to read this graph. The very first thing I want you to see is that on the x-axis we have temperature, and in this case temperature is measured in degrees Celsius. On our y1 axis we have altitude in kilometers, and on the y2 axis we have altitude in miles. Okay? So of the different layers of the atmosphere, if we are here on the surface of the earth, and that's what's trying to be represented right here with the trees and the mountains and the top of Mount Everest, okay, just to give you a reference point. This is that first layer that is going to be where we live, okay, the troposphere. And this is also where we are going to experience the weather that we experience here on Earth. Remembering that weather is something that happens on a more daily basis, whereas climate is something that happens when we talk about averages over a 20 to 30 year period. So the troposphere, what we know about the troposphere is that as we go up in altitude, the temperature within the troposphere is going to decrease. And that's what you're seeing here with this first yellow line. And as we cross over an imaginary distinction between the troposphere and the stratosphere, we're going to see the temperature change. So that distinction, that segmenting or the stratifying of the different layers of the atmosphere, the very first one that you're going to come across is going to be referred to as the tropopause. And then what you see is that the temperature starts to change. We start to begin increasing in temperature as we move through the stratosphere. Now, these two layers of the atmosphere are going to be the ones that we're going to focus on the most today, and the ones that are focused on the most within the AP exam. But just so that you're familiar, there is the mesosphere, and you'll see the change that is occurring here. We can get very, very cold. We're talking negative 100 degrees Celsius as we are transversing the mesosphere, and then eventually as we start to move from the mesosphere into the thermosphere and even into the exosphere. It's not listed here, but we go into the exosphere, which is the very, very top layer of our atmosphere. But again, these two are the ones that we're going to be referencing a great deal. If you are not already familiar with this piece of information, when we talk about the air that we breathe, so when we are intaking air as part of our respiration, the air that we breathe is a mixture. And that mixture then is made up of 78% nitrogen, that's that diatomic molecule of nitrogen, and 21% oxygen, that is that diatomic molecule of oxygen. And when you add those two together, the 78 and the 21, those are the primary components of the air we breathe. Now there is a very small sliver that's right in here. Okay, very small sliver. Usually it's about 1%. A majority of that 1% is argon. And the remainder of that then is going to be composed primarily of what we are thinking about a lot of times when we think about some of our greenhouse gases like carbon monoxide and methane. But you're also going to see small percentages of neon, helium, hydrogen, and krypton in our air. But make certain that you are familiar with these percentages going forward. Okay, so I don't know if that's something that you learned in a different science class, or maybe it's something that you're picking up for the first time here today. So understanding what the atmosphere is composed of is an important part of understanding what it is we do as humans to pollute the air that we are breathing. The other piece to this then is to understand, again, there's that reference, that Mount Everest reference as we move from the troposphere through the tropopause and into the stratosphere. When we think about air traffic, okay, this is again an altitude. This is about the area where we're going to have air traffic, when we are flying in our air traffic. So this area in here is where we're going to be focusing most of our attention today. Is going to be in the troposphere, but there is going to be a subject content when we talk about ozone when we reference the stratosphere and what it is that stratospheric ozone does for us. So do know and understand that there are two different types of ozone. There's, for lack of better descriptions, there is good ozone and there's bad ozone. And when we talk about photochemical smog as being one of our secondary pollutants, then that is referencing the tropospheric ozone. So that's going to be the ozone that's going to be down here closer to us, that's going to be created. We're going to talk about the chemical reactions that go into creating photochemical smog, this tropospheric ozone. This is what we're going to be seeing as brown, hazy, cloudy material, that yellowish brown haze that can occur, that can cause a lot of respiratory distress. Again, not a good type of air pollution to have. But then we have also what we call the good ozone, the ozone that we're going to find in the stratosphere. And this area of the stratosphere that we find our ozone layer is a very important part of the atmosphere, because this is the good ozone that is actually protecting us from UV light. So it is a shield, it's shielding us from UV radiation, and it's important. It is an important aspect of having life here on Earth, surviving UV radiation. So that ozone filters the UV radiation and keeps it from getting to us. So there's going to be a little bit of discussion today about the ozone layer and the hole in the ozone. And then there's more of this that's also covered when we get into global climate change. Okay, so most of what today is about is right in here, and we will touch on this aspect of it a little bit later. Questions before I go on? These are just some basic things. Again, things you probably are familiar with or you know about. Also, I want you to make certain that you are aware that there are 10 legislative acts that you are responsible for knowing for the AP exam. Those 10 legislative acts have been communicated in other parts of the course. One of those legislative acts is the Clean Air Act. And so I took this page, this comes right off of EPA.gov, okay, and it gives us an overview of the Clean Air Act. So you want to make certain that you understand when it was first proposed in the early 70s, and then also the amendments that took place to the major amendments that took place in the 1990s, and the impact on sulfur dioxide. So I'm going to be referencing some of this as we go along, but realize that the Clean Air Act is one of those 10 that you need to be familiar with. It's also one of your projects. It's an activity that we ask you to do in the second half of the course, is to identify those 10 legislative acts, and just make certain that you are familiar with each of those and a general description of them. So again, just if you haven't had the opportunity yet, go to EPA.gov, look up the Clean Air Act, make certain that you can sort of read through it and get a general overview. We're going to talk about it today from the perspective of the National Ambient Air Quality Standards. Okay, so again, this is the 1970s when the EPA is starting to establish these air quality standards. And those air quality standards are going to be around 6 primary criteria pollutants. Okay, and it's important that you know those 6. And they're listed here in an order that is easy for you to hopefully remember the mnemonic of SPLUNK, okay, S-P-L-O-N-C. So the first of the 6 criteria pollutants that are covered in the National Ambient Air Standard, which is again helping us set the standards for the Clean Air Act, is going to be sulfur dioxide. particulate matter, so this is typically abbreviated as PM, and this is also going to be part of what you're going to be studying when you do your air quality lab this semester. Lead, again, you might not think about lead in the atmosphere. You may not think about lead as being a primary pollutant for air quality, but it is, and it's the P. Okay, it's, well, let me rephrase that. It's the L in Splunk, but you should know that the symbol for lead is PB. Ozone, this is going to be that tropospheric ozone. This is going to be the bad ozone and not the good ozone. So this is going to be that tropospheric ozone and the photochemical smog that we're going to have in the troposphere. We've got nitrogen dioxide and we have carbon monoxide. And when you guys look at those 6, tell me what chemical compound, what gaseous chemical compound you may be surprised is not covered. Just type in what you think is surprising that it's not covered in the Clean Air Act. Just curious what you... I'm curious to know if you're surprised it's not here. We talk a lot about it in AP Environmental Science. Somebody just hazard a guess for me. Well, what's the one that you... Okay, I see Abby responding. What's the one? Yeah, CO2. It's CO2. CO2 is not covered in the Clean Air Act, okay? It's not one of the 6 criteria pollutants. And so typically there is at least one question in the multiple choice part of your AP exam that is going to ask you, do you really understand what those 6 criteria pollutants are? And a lot of people want to move towards carbon dioxide, and I just really, again, want to make certain that you see that it's not here. It's not in this process, okay? All right, so when you go to your AP classroom, and don't forget that you have the opportunity with your ELOs, with your extra learning opportunities, you have the chance to go through and take some of the practice quizzes that we've set up, we've built. And what we're trying to do there is encourage you to use not just the modules within the Georgia Virtual School course, but also the AP Classroom and these AP Daily videos. These AP Daily videos, these are videos that have been made by College Board. I know Mrs. Madden's talked about them. I've talked about them. They were brand new last year. And we just really want to emphasize to you how important it is that you're using some of the resources that College Board is providing to you. If they are the makers of the exam, they're telling you this is the content that's going to be on the exam. So as AB students, you're going to finish this course in December. But when you get ready to start studying, hopefully in March and April, in preparation for the May exam, you're going back and you're utilizing these AP Daily videos to assist you. So what you see here is the very first set of AP Daily videos that are listed under Unit 7 in the AP Classroom and Section 1, which is Introduction to Air Pollution. And you'll see here that the video introduces primary versus secondary air pollutants. So we're going to talk about both of those because it is important that you understand the difference and how one is created, how one is used to create the other. And then also, again, those criteria air pollutants that I've just referenced for the Clean Air Act. Okay, so let's go ahead and take a look at this picture. Well, okay, let me talk first and then I'll have you take a look at this picture. So what is the difference then between a primary and a secondary pollutant when we're referencing air pollutants? Well, in general, air pollutant is anything that is going to be harmful to humans, right, or harmful to the environment. Now, I have just used a bunch of words that we encourage you not to use in an FRQ. So hopefully you've heard us recently as we've talked about the different types of FRQs and as we've shown you some of the Mr. Smead videos, that it's not enough for you to say air pollution. That's not detailed enough. So while we're using it to initiate our definitions here, it is really important that you start to drill down into some of the more specific pollutants, that you're referencing these pollutants and not just using the term air pollution or not just saying that it's harmful to humans. Again, we need you to be going beyond just this general definition. So when we look at a primary pollutant, then this is going to be a pollutant that is going to be emitted directly into the atmosphere. So you typically can see it both usually as a point source pollutant, also too as a non-point source, but primarily as a point source. And so these are the things that you want to consider, that there are both natural and anthropogenic. And again, if you are not familiar with this term, anthropogenic, that is meaning human caused or human created. So you have natural primary pollutants and you have anthropogenic primary pollutants, things like volcanic ash. The term VOC, you're going to see this a lot, not just in this PowerPoint today, but also in future module content. A VOC stands for a volatile organic compound, a VOC, and typically what you're referencing here are carbon chains, long carbon chains that are volatile, that are organic. Okay, so volatile organic compounds in this case that are being given off by plants if they're natural. And then the anthropogenic, these are a primary pollutant would be carbon dioxide. Now sometimes you're going to see this term NO and then the subscripted X. We're going to say this is a NOx. Okay, it's kind of a short term for many of the different types of nitrogen oxide components that are created and emitted to the atmosphere as a primary pollutant. And here you have sulfur dioxide, and we're going to talk about sulfur dioxide today in terms of the acid rain. But you can also talk about NOxes and SOxes, okay, where this little, instead of just the 2, maybe you have a 3 here, so to call them generically an SOx would just infer to the reader that it's a combination of the different components that are there. So those are your primary pollutants. Your secondary pollutants then are going to form once they are in the atmosphere. They being, once the primary pollutants go into the atmosphere, then a secondary pollutant is going to be created from that primary pollutant. Okay, so it's going to be a primary pollutant that is maybe reacting in combination with water vapor in the atmosphere or with some other type of atmospheric gas. And these are going to be examples of your ozone or your acid rain. So this is one of the best pictures, I think, that if you take the time to study, and I have seen different versions of this. This is the one they happen to use in the AP Daily video, but there are other versions. There's a really good version of this in your e-text, okay? So it's available to you. If you are studying air pollutants and you're trying to do a quick review, go to this visual. Use this visual, because what it's doing is it's showing you that you have natural components, you have stationary anthropogenic components, and you have mobile anthropogenic components. Okay, so all 3 of these, right? Stationary, mobile, and natural. These are going to be the list of primary pollutants that College Board is going to expect you to know. Now, are all of these included in those 6 criteria out of the Clean Air Act? No. There are more here than the 6 that are listed, but you've got carbon monoxide, carbon dioxide, sulfur dioxide, nitrogen oxide, nitrogen dioxide, most hydrocarbons. So notice it says hydrocarbons here, but this is where I would infer a VOC, a volatile organic compound, and then suspended solids. So suspended particles are suspended solids. This is soot and particulate matter. This is going to be the lead that you're going to find in the atmosphere. All right, so these are your primary pollutants. Again, these guys are then going to go through some sort of chemical reaction, and from there I'll use the example of sulfur dioxide. Sulfur dioxide is going to react with the oxygen in the air. Remember that 21% we mentioned earlier? And it's going to combine to form sulfur trioxide. And then what's going to happen is that sulfur trioxide is going to react with moisture in the air, and it's going to form sulfuric acid. So you've got H2O coming together and reacting with the sulfur trioxide to make sulfuric acid. And so you can have this sulfuric acid fall as acid deposition, or you can have this sulfuric acid fall to the ground as acid rain. So that would be an example of how sulfur dioxide, a primary pollutant, is turned into a secondary pollutant in that process. Okay, any questions before I move off of this slide, because this is a pretty critical slide for us as we go through the information. Anything that you have questions about? know and be able to interpret that picture. This is the same thing in words, okay? I'm not going to go through all of it again. I'm just trying to show you then where some of those sources for those primary pollutants may come from. Most of them you'll see though are going to be combustion. So some sort of combustion, whether it be from a fossil fuel or for an automobile, even if you're burning wood, or if we're burning coal, particularly if we are burning coal in a power plant to produce electricity, you're going to see sulfur dioxide as one of the primary pollutants. And then here are those secondary pollutants, the ones that are going to be of particular interest to you today when we talk about how the ozone is formed. And then this one right here, I don't want you to worry about the name of this because this one gets abbreviated as PAN, P-A-N. You're going to see this a little bit later in the PowerPoint. So this is the peroxyacetyl nitrate. Okay, but it can be easily abbreviated as PAN, and this is what we're running into when we get into some of that photochemical smog. All right, let's keep going. Oh, why are we not advancing? Here we go. Okay, now the reason for also talking about particulate matter is because this is going to relate directly to the air quality lab that we're asking you to take a look at. We've rewritten that lab for you this summer. And it's a little bit different than what we've looked at in previous years. So again, I want to focus on this particulate matter. This is again another picture that has come from EPA. This is a very interesting picture, I think, because it gives you an idea of how particulate matter is classified. So much like our soil, we were talking about the soil lab a little bit earlier, and we talk about the size of the particles of the soil. So too then do we talk about the particle size of particulate air pollutants, okay? And so there's two different categories that we break these into. We've got PM10, so again, this is particulate matter with the subscripted 10 and particulate matter with the subscripted 2.5. And this is talking about micrometers, okay? So micrometers, the size being, if you think about the size of if you think about your prefixes and you're thinking centimeter and then millimeter, and then a micrometer is just below the millimeter. So there's 1,000,000 micrometers in a meter. This is explaining to you how small this really is. So if we compare, and by the way, this symbol right here, I don't know if you can see it in the slide presentation, it's the Greek letter mu. So that is 90 micrometers. That's how that prefix is shown. This would be then a particle of sand, like beach sand, and this would be the cross-section of a piece of human hair. Okay, so it's trying to show you in reference to other very small things how big particulate matter is if it's PM10, all right, or if it's PM2.5. Okay, and so we're not talking very large particles here at all, but this particulate matter can be very it can be very costly to humans. It can almost be deadly in some cases as far as respiratory distress if we are breathing in a lot of particulate matter. So that's why you see particulate matter as one of those 6 criteria. When it's the P in particular, it's the P in the splunk that it's so important to understand the size and the impacts of taking in particulate matter that's in the air and what problems that it can create for us. So you're going to see this related then to that air quality lab that we've added into the course this year. And you're going to be, I'm going to talk about it towards the end, but you're going to be developing your own design of experiments. So again, working towards developing DOEs, design of experiments, so that you are better prepared to answer the FRQs on DOEs. You're setting up your own experiment using 3x5 index cards, And again, I'll show you the setup a little bit later, but you're going to be letting these index cards set out depending on what your criteria is and your hypothesis. And you're going to be seeing how maybe you're testing a room or a kitchen or a bedroom where an animal may be present often. And you're going to be capturing that particulate matter that's in the air. You're going to see how much of it is going to be captured on your card, and you're going to count it, and you're going to set up your DOE to capture that and make some comparisons. So it's part of why I made certain I included this picture in our discussion tonight. Okay, I'm looking at our time. And I'm going to go through a couple of these questions pretty quickly because there's some other things that I want to make certain that we get to. But these, we're always trying to show you some examples of multiple choice questions or FRQs that you're actually going to see on the, examples of what you might see on the exam. And again, what we're looking at here is that in this particular example, this would be an FRQ where they would ask you to read a graph. All right, read a chart. Lots of charts, lots of graphs on the AP exam. And so we're trying to give you opportunities to practice. So here you have these 4 categories: nitrogen oxides, those are those NOxes; sulfur oxides, those are those SOxes; the volatile organic compounds, and the particulate matter. And this is atmospheric pollutants that are in Canada. Okay, and so you have both the 2006 industrial air emissions, and then what the projected air emissions are going to be under the new plan. Okay, and so in this particular question, it says that Canada has proposed an action to address climate change and air pollution, and the action will reduce the impact of greenhouse gases and pollutants on the environment and human health. Which of the following claims? So now you're talking about claims, right? In our science practices, we need to be able to identify claims, either from an author or from the data. What is it that can be claimed from the data? So which of the following claims about the Canadian Action Plan is best supported by the data in the graph? And when we look at this, I made this way too small. We're looking at part C. The plan supports phasing out traditional power plants, okay, and transitioning to sources like hydroelectricity, wind, and solar power. Well, why is it they would do that? What they're trying to demonstrate is that under the new plan, we want to reduce the amount of compounds that are going to be as part of our pollutants. And by doing so, by phasing out coal burning power plants, we're actually going to see a reduction then in the amount of air pollutants such as nitrogen oxides, such as sulfur dioxides or sulfur oxides. That's where we're going to see some of the biggest changes, okay? Some of the biggest changes that are going to be as a result of that plan. So that would be an example of one that you might think about. The other reason that I stuck this question in here so that we could take a look at it, how many of you normally if I were in the classroom I'd say raise your hand but kind of give me some feedback in the chat room. How many of you may be responsible for pumping your own gas or purchasing your own gas? Say you're driving, you've got your driver's license. How many of you actually have had to fill up your own gas tank? Not necessarily pay for it, but just the action of filling it up. Have you ever pumped gas yourself into your car? Okay. And so when you walk up to the gas pump, right, you look at what's there. Usually there's 3 different choices, right? There's high octane, lower octane, so it goes anywhere from like 87 to 93. But do you notice that it is referenced as unleaded? Do you notice when you're at the gas pump that you see that it is unleaded gas? Has anybody ever noticed that the gas that you are purchasing in 2021 is unleaded? And the reason I asked that question is because in the 1970s, the gasoline that we put into our gas tanks was leaded. Okay, so in the 60s and in the 70s, the gasoline that was being used had lead in it. And what we were starting to see was lead emissions from the combustion of our leaded gas, where lead was actually starting to build up on the sides of the road. And so as a result of what we have seen, and then making and enacting the change of taking the lead out of our gasoline, we have here in the United States from 1970 seen what? A very dramatic decrease in the amount of vehicular lead emissions in the United States. And again, it's because we took lead out of the gasoline. So when we look at this question, which of the following best explains the cause of the trend shown in the graph for lead emissions? All right, we're going to be looking to see that unleaded gas right here was first introduced in 1974, and that amendments, so there are those amendments to the Clean Air Act, required cars with models that were older, that any model made after 1975 or later was going to only use unleaded gas. So that again, was lead one of our Splunk criteria pollutants? Yes, it was. And this is how, through amendments to the Clean Air Act, that the United States has addressed lead emissions. So I want you to be familiar with that, okay? All right, moving on. I want to talk a little bit, any questions before I go further? Anything else that you guys might have? Because this next piece is pretty hefty, okay? When we talk about photochemical smog, there's a lot that we want to be able to discuss with regard to the chemistry associated with it. So what I've done here is not only have I shown you, in the AP Classroom Unit 7, okay, these AP Daily videos. So this is section 2 now of the AP Classroom Unit 7. This is going to be addressing photochemical smog. So you see video 1 and video 2, it's going to detail the formation of the photochemical smog, including the chemical reactions that transform those primary pollutants into those secondary pollutants. So remember, the difference is that secondary pollutants are formed from those primary pollutants. And then the second video is going to talk about the human health impacts of photochemical smog, because there are negative impacts to our health as a result of this type of smog. Now, I know that this is a whole lot of words, and normally I try not to put this many words on a page. But what I want you to see is that this is the information, okay, that is just that is required for photochemical smog just in Unit 7 in Section 2. So this is sort of the what you need to know list, okay, when it talks about photochemical smog. This information comes directly from the course and exam description, which can be located online, but this is also what is included in your AP Classroom when it starts giving you some of those topics. All right, and so I use this in many cases to just sort of direct students as to what it is that they need to know in preparation for the actual exam. We're also going to talk a little bit about something called thermal inversion and the impact that that has on air pollution. Okay, so this particular picture is going to help you sort of break down the concept of industrial smog and photochemical smog. So we're going to talk about this visual first, and then I'm going to show you this picture. The next slide, okay, I'm going to show you this slide, and this is going to come directly from the AP Classroom. This information, again, is also very well documented in your e-text. Okay, so please make certain, in those guidebooks that we provide you, and at the very beginning of the semester, we gave you the reading list for the material that was necessary to what you needed to read in your e-text to be successful in this course. So if the material that I go over with you today, if you really feel like you didn't grasp everything, you want to go back and review it again, you want to be spending that time, I believe it is your chapter 15, okay, and module 47 in your textbook. So there's content there in the textbook about the photochemical smog. All right, so industrial smog, where is it, first of all, that we get this term smog? Okay, my mouse is not cooperating. Here we go. Where do we get this word smog? Well, it's going to be a combination of smoke and fog, right? And industrial smog is going to be caused primarily by the burning of coal. So we're going to get a mixture of soot Soot's going to be part of that particulate matter that we were referencing earlier. We're going to get sulfur compounds, okay, from burning coal. In fact, one of the things when we look at coal, we try to determine and understand what its sulfur content is, because sulfur dioxide can be a problem as an emission from coal burning power plants. And then water vapor, okay? So mostly during the winter, we're going to see industrial smog that's going to occur in the colder winter months, typically in countries like China or India or Eastern European countries where they may not have some of the environmental standards of using scrubbers to scrub the material, to scrub the content before it is emitted into the atmosphere. And so again, this would be an example of our industrial smog. But then we get into this term photochemical smog. So these are emissions that are caused by motor vehicles. Okay, so this is what we're going to be talking about right in here. Our motor vehicles, we can find some coming from industrial facilities and from power plants, but I'm going to focus primarily today in our discussion around motor vehicles. Okay, the combustion burning engine of the number of cars that are on the road. What happens is in the burning of that fossil fuel, we produce nitrogen oxides and VOCs as part of that vehicle exhaust. And then what's happening is that the sunlight has a lot to do with how those primary pollutants are converted into secondary pollutants. So think about a car. A lot of cars, people maybe in a city like LA, because LA always seems to be the example that is used when we talk about photochemical smog. Lots of cars on the road, lots of sunshine, lots of warm temperatures in the afternoons. So you have cars, people who are driving their cars in their morning commute, and you have those nitrogen oxides and you have those VOCs in the exhaust. And in the morning, what is happening then is that the sun is coming up, and the UV light that is coming from the sun itself is actually going to break down the VOCs and the NOxes into the photochemical smog that we're going to refer to as our PANs and as our tropospheric ozone. And so then what happens is that fog and those smoggy yellow brown conditions kind of hang there in the air, right? And they don't dissipate until much later in the afternoon and into the early evening, when the temperatures start to come down. And it is this material right in here that we're starting to again refer to as that tropospheric ozone. So now let me show you this particular breakdown. Now it looks to me, when you first see this schematic, to me this looks a little overwhelming, but if you will take the time to go through and watch that AP Daily video, I personally, as an AP Environmental Science teacher, think that this is one of the best overall descriptions of how photochemical smog is actually produced, because it's giving you 2 or 3 different ways to think about it. Okay, so you've got the picture that I just gave you here. Okay, so you've got a visual there. You have this schematic, okay, and this flow chart. So this is the second way that you can study how photochemical smog is produced. And then you have the actual chemical reactions that are taking place. So let's step through this. Again, we've talked about LA as an urban area with many, many cars. So this is going to be our primary source, right? Our primary source of photochemical smog. Well, what's happening? These cars then are burning fossil fuels. And they are emitting from the car itself these nitrogen oxides and the volatile organic compounds, the VOCs. So these are our primary pollutants. Now, within the troposphere, there are some very specific things that are going to, there are some conditions that are going to enhance the production of our secondary pollutants. And again, that's that sunlight, because we need that UV light to help break some of the bonds within the chemical compounds, and you need that heat. So you need UV light and the heat. So those are the conditions that we're going to, there's environmental factors that are going to make this occur. And from the combination of your primary pollutants and the environmental factors, this is how we go about producing ozone And again, there's that PANS, that is abbreviation for the peroxycyl nitrate. So this may be what you choose to study in order to understand how photochemical smog is produced. I will also say to you, though, that there is a very good picture, visual picture in your text, your e-text, that I have seen in some examples of FRQs, like practice FRQs, okay? So again, it depends on the type of learner that you are. But you do need to know the chemicals. And I'm not saying that you have to be able to be an expert at the writing of chemical equations, but you need to understand this particular piece right here at the very bottom, okay? So our NOxes, our VOCs, what's happening, they're going to react with oxygen in the air as a result of that UV light. Well, what is it that the UV light's doing? This UV light is helping to break the bond in our nitrogen dioxide and allowing an extra oxygen to be available, not as a diatomic molecule, but just as an atom of oxygen. Well, that spare atom of oxygen then is easily attached to, in a reversible reaction, with just the regular O2 that's in the air. And when we take that spare oxygen and we combine it with that diatomic molecule of oxygen, then that's how we're going to get that tropospheric ozone, that bad ozone. Not the good ozone, but the bad stuff. Okay, and so understanding the role of UV light and the splitting off of that oxygen and the recombining of that oxygen with that oxygen atom with the O2 to form ozone, that is something that you do want to be familiar with. So again, in summary, you got your NO2s, you got your VOCs, you've got oxygen in the air. That oxygen in the air then is going to be broken up and be involved in the creation of the ozone, the tropospheric ozone, and those PANs. So I'm going to take a deep breath and ask you what kind of questions might you have about that photochemical smog. Is this something that you feel like you could describe if you had to? Is this something that you need to go study a little bit more about? Have I given you enough resources to talk about it yet? I see a couple of you typing to me. So when we say to you that don't talk about air pollution, right? And when you're writing an FRQ, don't just say air pollution, that you've got to be specific. It's not that you have to write a whole lot more words. We just need those 2 or 3 sentences to have more detail in them. Okay, so it's like, that's, if I go back to the very first slide and talking about air pollution, it's not enough to say just air pollution. You've got to be able to at least reference something like this. Okay, be able to go back. So hopefully going over this very detailed process and giving you the resources like the AP Daily video, like the textbook, will help you in your preparations. And then of course you've got those ELOs that we've provided to you for extra learning opportunities. You can take your quizzes. That's another way to help study for the actual exam. But this is the type of detail that you're going to want to be familiar with. Okay, and don't hesitate to reach out to myself or to Miss Madden when it comes to better understanding beyond what we cover here today. Okay, let me keep going. The reason that I put these graphs here, again, I want you to pay attention to how to read graphs and what it is that this information is providing to you. Lots of the opportunities on the exam to actually interpret the graphs themselves, but what is here on this x-axis? Okay, let's think about the term photochemical smog and why we might be paying attention to the times that are located here. What did we say earlier that we need? What are the environmental factors? We need sunlight and we need some heat, right? So this is the time where the commuters are getting up in the morning, they're getting into their cars, and they're going to be doing their driving. And as the afternoon as the mid-morning to midday time period comes around, your sun is rising, the temperature is increasing, and you're going to start to see the production of different types of components that are going to make up the primary and the secondary air pollutants. And so this particular question, and the one just behind it that we'll go over as well, this is the data then that was used to create the graph, was collected in the winter. Okay, so this is still wintertime, right? Which of the following best describes how the graph would be different if the data was collected in the middle of the summer? So what do you think might happen to something like this line right here? What if one of these is your nitrogens, and one of these are your ozones, okay, your ozone? What do you think is going to happen in the summertime if there's even more sunshine and more heat? Well, hopefully you see that the concentration of component C, okay, so here's component C right here, that in the summertime this is going to be even more pronounced because of that UV component and the heat that is required. Okay, all right, so that's just trying to get you to practice reading some of the graphs. On this particular one, which of the curves on the graphs depicts the concentration of ozone? So based on what we just said, hopefully you see that it's this one right here. Okay, so that should be C. So this C is the ozone. It's what's going to be formed as a result of that UV light. And then this one, they're a little nicer to you. Can you see why they're a little nicer to you? Because they've actually labeled the curves. All right. Remember what I said earlier is that a lot of times with your hydrocarbons, you need to interpret hydrocarbon as a VOC, as a volatile organic compound. And then you have both your nitrogen oxide, your nitrogen dioxide, and then you have, again, that lag of that ozone. So in this question, if technology that reduces the hydrocarbon component, this part right here, all right, if we can reduce the VOC component has been utilized, if we are utilizing catalytic converters, or we are designing cars that don't burn fossil fuels, if we can use technology to reduce that hydrocarbon concentration, which of the following would most likely, what would be the most likely result? All right, so hopefully you see that it would be that we would see lower ozone, again, lower tropospheric ozone as a result. All right, now I want to talk to you about moving from photochemical smog into the concept of an inversion, a temperature inversion. And this is a weather condition that can occur that can cause a lot of problems. And they've caused problems in the past. Some very famous weather inversions that have occurred took place in England, in London, in the early 1950s, where what happens is typically we know that this warm air, okay, over here is going to be rising. So we've got our air rising, but we also know that as that air rises, it starts to cool. And typically we see, a layer of warm, and then a layer of cool, and then a layer of cooler. And particularly as we move up into the troposphere, that's what we saw from that very first picture. That the temperatures are going to decrease as we move up in altitude. What can happen though is that warm layer can kind of start to rise up and settle. Okay, it can settle right in here, and in this example they're trying to show you that it's like in a valley. All right, so this is happening in a valley, and this warm layer right here almost starts to act like a blanket. And that blanket then of warm air is going to keep what is happening here in the city. So either your car exhaust or your industry exhaust, it's going to kind of keep that air pollution that is occurring, those emissions, is going to keep them sort of concentrated in this area right here. And it's not going to allow them, this layer of warm air is not going to allow them to dissipate into the atmosphere. So it's that rising warm air then that is going to inhibit the dissipation of that air pollution, and that's what we're referring to as that inversion. So again, one of the more famous examples that I mentioned was the one that occurred in London. I mean, thousands of people died as a result of the inversion. So think about 1950s. They were using it was in the late winter, early spring. They're using coal to burn in their homes to heat their homes, and a weather pattern arrived and sort of developed over the city of London, and this warm layer of air kept all that gray smoke, all that soot, all that particulate matter, it kept it just sitting here hanging over the city of London for a couple of weeks. And as a result of that, again, just the number of deaths, the amount of respiratory distress and the number of deaths that occurred was significant as a result of that inversion. So that's a very famous weather event that has occurred that impacts air pollution. So then this would be an example if you were to see, this is a real test question or a practice question. Here's that warm layer of air that's acting as the inversion, and what's happening then is that you aren't getting as the depth of mixing in the atmosphere is not as significant. So it's acting again as that blanket and keeping all of those emissions sort of just hanging there over the city. So this would be another picture of the atmospheric thermal, and many times again called a thermal inversion because of the temperature differences that occur. In this particular question, if the air layers in the diagram were relabeled to illustrate normal atmospheric conditions, what would we expect? Well, we would expect this to be warmer, this to be cool, and this to be cooler. Okay, and so when we look at that, we would want it to be B, would be the correct answer for that one. Okay, acid rain. Let's see if we can wrap this up with our acid rain and get you guys out of here. So now I've moved into section 7, all right, of the AP Classroom Unit 7. So section 7 of Unit 7. And this is going to be talking about acid deposition and acid rain. Okay, so the things that you want to know about how those primary pollutants then can react with the water in the air, the moisture in the air, to cause the fallout, the precipitation of acid rain, and the impacts that it has, both on soil and on aquatic systems. All right, so if we look at this picture, again, we have both anthropogenic and natural pollutants, primary pollutants. Okay, so here are those VOCs, the SO2, the NOxes. We've got mercury. Mercury is also something that is of concern to us when we are burning fossil fuels, particularly in power plants. And then you, of course, as we mentioned earlier, VOCs that can just be emitted by trees. Think about a pine tree and turpentine, some of the resins that would come from a pine tree. That would be an example of a VOC that is emitted naturally. So you have sources. I'm going to follow this guy right here. I'm going to follow sulfur dioxide. It's being emitted into the atmosphere, okay, as a gaseous pollutant, as a primary pollutant. That primary pollutant then can react with water in the clouds, and it can precipitate out as wet deposition. But it can also just fall, the sulfur dioxide can fall as a dry precipitate, is a dry deposition that can occur. And so if you can imagine that you have rainwater that is typically acidic to begin with. So if water is naturally a pH of about 6.8, and rainwater itself before any additional sulfur dioxide is going to be probably in the 5.8 to 6.8 range, so ever so slightly acidic. but you introduce sulfur dioxide and sulfur trioxide to that atmospheric moisture, and then that water is going to become much more acidic because of the addition of the sulfur dioxide. So you're actually forming sulfuric acid. So if this falls to the ground, you're basically spreading sulfur dioxide that's been made into sulfuric acid either directly onto the trees, or maybe it's going into the soil. And if it goes into the soil, then it's going to start causing pH problems in the soil. Or if it goes into the pond, it's going to start causing pH problems in the pond, a lowering of those pHs, things are going to become more acidic, and the ecosystem, those species that are present in the ecosystem that are, within a range, that need a range of tolerance of their pH in their environment, they're going to be affected by things that are occurring with regard to acid rain. So you want to be able to talk through that concept. Okay, let me see if I can get this. There we go. All right. So this particular question that comes from AP Classroom and comes from the question bank, it's asking you, do you understand the concept of pH? Remembering that pH is on a scale of 0 to 14, where 0 is extremely acidic and 14 is very, very basic and 7 is neutral. But every time you go from one, I'm going to start over here at South Pacific. Every time you go from one unit of pH, so say you go from a 5.4 down to a 4.4, because pH is actually on a log 10 scale, that's not just one unit of pH, that's actually a change to the power of 10. So 1 unit change on the pH scale is equal to a power of 10 change. And if this had gone then from 5.4, not down to 4.4, but down to 3.4, so if it had gone from 5.4 to 3.4, then it would have been, again, as a log 10 scale, 10 times 10. So it would have been 100 times more acidic when we talk about the pH scale. And so that's one of the things that when we talk about acid rain and the pH of precipitation, particularly around the world, notice here you see the northeastern United States, so very heavily populated area, particularly if you're thinking about areas of West Virginia and Pennsylvania, where you're going to have a lot of coal mining that is taking place and coal-powered power plants to generate electricity. We're going to see then the pH of the precipitation be 10 times more acidic than, say, something that would be in the South Pacific. And that is the purpose of that question, to be able to talk to you about pH, the log 10 scale of pH, and the impact of acid rain that comes from that primary pollutant turning into a secondary pollutant. I would encourage you to take some time. I'm not going to do it now, but this would be an example of an FRQ where you could look at, again, practicing reading a graph and utilizing these task verbs of describe and identify. You look here at the years going from 2001 to 2018, and this particular data is showing us the pH of the rainwater. And this is going to be showing us then the consumption of coal in millions of tons. And as we start to see the decline in the coal consumption, then we start to see an increase in the pH of the rainwater. And that is because if we're reducing coal, then we are reducing sulfur dioxide and NOx emissions from the reduction in the coal burning, and you're going to see the impact then of that on the rainwater in local areas. So you could use this to practice completing an FRQ around atmospheric pollution of acid rain and the impact on the pH of the rainwater. All right, I am going to not talk about this today just from the because of time. I think we're going to save this and I'll talk with Miss Madden. This is a pretty important concept when we talk about so far up to this point, I've talked about tropospheric ozone, but this is starting to talk about stratospheric ozone. And I'd like to go ahead and just leave it as a separate topic as we get closer to the end of the semester for you when we discuss climate change. Okay. If you're interested, just this is where stratospheric ozone helps us in the filtering of UV light, particularly UVC, which is going to be the more damaging of the UV radiation. All right, lastly, and this is going to lead into the lab, you have everything that we've talked about up to this point being air pollution, which is outdoor air pollution, but you also have this stuff called indoor air pollution. And this particular picture coming from the EPA just provides you examples of indoor air pollution where it can be found around the home. One that you may not be familiar with that you want to familiarize yourself with is the emission of radon. Radon is a gas that can seep up from the ground if there is radioactive elements that are in the ground itself. And this radon gas can be detrimental to health if it is emanating through the basement of your home. So it's seeping through the foundation. So radon, again, radon gas, because it's a carcinogen, it causes cancer. And so many people, particularly up in the Northeast, they will have basements. You know, I live on the coast of Georgia. We don't have a lot of basements here, right? Because, you know, we dig 10 feet down and we hit water. But if you live in an area of the country where you have a basement in your home, many people will put a radon detector in their basement to detect radon because it's odorless, colorless. You don't know that it's happening, much the way you would have maybe a carbon dioxide monitor as well. Cigarette smoke is obviously something that is an indoor pollutant. Okay, so again, we're talking about particulate matter from that cigarette smoke. So secondhand smoke, if you're breathing in someone's secondhand smoke. So again, animal hair and dander, these are all particulate matters that can be found in the home. Well, how does that relate to the lab? Okay, I'm going to show you this particular, okay, how does this relate to our air quality lab? You want to be studying indoor air pollution. It's going to be specific to indoor air pollution. It's going to be asking you, this lab is going to be asking you to design your own experiment. So the air we breathe is not solely made of the various gases that we've discussed, but it's also carrying that solid particulate and liquid droplets that we call PM. And that humans can inhale this. And remember, we talked about how small some of these particles are into the lungs, and these particles can be embedded in the lungs and they can remain there and cause pretty significant lung damage. So we want to understand where some of the different types of air particulate can come from. And so we're asking you to do your own design of an experiment. You're going to set up your experiment where you have these 3.5 by 5 cards, and you're going to have 3 of them, a minimum of 3 of them. One of them will be your control, and that control is going to go into a container with a lid on it, meaning that it's not going to be exposed to any of the air that you're testing. And then I'm just going to throw some examples at you. Maybe you put one of those cards in a bedroom where the animals are located, and maybe you put one of your cards in the kitchen. Okay, or maybe you have a smoker in the home and you put one of those cards in a room where that person may smoke inside. So those are just some examples of what you're going to, the different types of air that you can test. You're going to make a hypothesis that justifies why you think the experimental groups will have more or less of the particulate matter than the control group. Okay, and you're going to want to be focused on designing your experiment with the aim to eliminate as many of the different types of variables that can cause you problems. Okay, so you're really wanting to focus on your controlled variables. And this is not going to be a full lab report. This is going to be a mini lab. And when I show you some of the examples of what you're going to be asked to provide, this is in the rubric that's included. So for the lab report, not a full-blown lab report, but you're going to include your hypothesis, your data table, you're going to graph your data, and you're going to complete an analysis and a conclusion question. And please don't forget your references. Okay, don't forget about these. These links that we have here, this is actually going to take you to the picture that I showed you earlier. And here are your materials that you're going to want to use. This is an example of your index card. You're going to want to draw both of these squares on each of your index cards, and then you're going to use a small amount of Vaseline, or maybe chapstick if you don't have Vaseline, or maybe, you know, like Burt's Beeswax or something, but something that's going to be sticky, right? A real thin layer of Vaseline that you're going to put over both of these squares. And you want it to be inside the square, right? And it's the area that is important. Okay, so here we have one centimeter squared, and here we have 3 centimeters squared. And you don't know which one of these you're going to use until you actually conduct your experiment. Okay, so you want to set your cards up. And by the way, right here, this is a great video from a individual. It's an AP teacher. Her name is Christy Schertz, and she provides a video to give you an idea of how to put your cards together. You're going to put those cards in your different areas, however you choose to set up your DOE. And when you come back 2 to 3 to 4 days later, you're going to talk about your quantitative data. You're actually going to count the particles, right? What is it that you captured on these cards? Did you capture dust? Did you capture cat hair? Did you capture an insect by chance? Okay, so you're going to have both quantitative data and qualitative data, and you're going to write up a paragraph of your analysis that is analyzing the data table and your graph that you'll build. And then also in your conclusion, you're going to want to be able to explain the limitations of your experimental design and the possible sources of error and how you would go about improving that going forward. Okay. And then the very last thing I'll leave you with, these are some examples of some possible, graphs. Your graph doesn't have to look exactly like this. If you were doing this lab as a group of people, okay, so maybe you had 3 or 4 people in your group, then you would have each person read the cards. So each of these people are actually reading the cards themselves, and then you're collecting this information. Okay. If you obviously you're not doing this as a group, you're not in a classroom, you're not doing it as a group, so maybe you want to enlist the assistance of a friend or a family member to help you, gather additional data about the cards. So let me stop here. I'm sorry I went over the 10 minutes, but what other questions might you have about the content? Or any questions about the lab? I see Abby, Deborah. Okay, no questions. Okay. Just want to make certain that we're addressing. Again, I think you guys are about 2 to 3 weeks ahead of my classes. I don't have any right now, but I will go over it when it gets closer to the lab. Yeah, we're trying to be a little bit ahead of you guys and making certain that we're giving you that we're not behind you in the delivery of the information. So then the next 1 or 2 weeks of live learning sessions, we will be together again, talking about the different types of questions that you're going to be encountering. We're going to be doing some more math in preparation for the AP exam, and then I'll do at least 1 more of these live learning sessions, but instead of doing air pollution, it'll be on water pollution, but it will also specifically talk about the lab that we call poop on the poop. Okay, and when we say poop on the poop, we really mean poop. So we'll be going through the impact of how a water reclamation plant is put together. okay, because that's another part of the exam, another part of understanding how do we address emissions, water emissions. Okay, so I've kept you long enough. Let me stop my